Hey everybody, welcome to the channel. Can the new high temperature PLA from Polymaker print good airplane parts without the hassles of the other materials? And can it pass the hot car test? Using my aerospace engineering degree, 30 years of product development and 3D printing, and 5 years of designing the fastest 3D printable RC airplanes, with the help of my 20-year-old truck on a hot day and some ingenuity to decide if I would recommend using this new material to print my airframes. I am not affiliated with Polymaker in any way, and I purchased my spool because I love to try out new materials, figure out how to make them work, and share my results so you can spend more time flying. Thanks for watching. Please like and subscribe. And check out my other videos about printing, different materials and testing, and flying these SoarKraft designs to the limits of what's possible. This channel is funded by viewers like you purchasing my files on my website for printing planes just like this, and helps me to continue to refine, develop, and share new ways of making them better, faster, and cheaper to hopefully benefit everyone. Or at least to have a good time. Nice. "3D printing airplane parts with regular PLA and PLA Plus is pretty straightforward. Most all 3D printers can do it. Strong and easily prints accurate parts, but has the lowest heat deflection temperature of the common printing materials. So don't get it hot, which is pretty easy to do in the sun with the wrong color. Or in a hot car before you get the AC running. Sad, destroying a plane just getting it to the flying field. PLA's low heat deflection temperature falls well within the achievable hot car range. PETG is a little bit better, more heat resistant, but still well within the range attainable on the hottest of days. These other materials require another level of effort to get good parts. Higher nozzle temps, higher bed temps, warping parts, smells, toxic fumes, all of which can be dealt with using the right equipment, like vented enclosures, or the printer upgrade you've been wanting. But this all costs money, and not all of these have the best mechanical properties. So instead of this, an easy-to-print, high-temperature, non-toxic material would be a game changer. At first glance, this new Polymaker high-temperature PLA material sounds awesome. Effortless printability and stable up to 150 degrees C, which would take it from down here on the temp chart to way up here, and no fancy printer necessary. But their examples and test data are based on solid multi-wall parts, not thin wall structures. And even though their description states it can maintain its shape up to 150 degrees C without sagging or deforming under its own weight, in the same spec sheet the actual heat deflection temperature is much lower, like only marginally better than regular PLA. So I guess I need to figure out which value matches how these actual airplane parts behave when you get them hot. If this material is dimensionally stable up to anything close to 100 C, I can try annealing, which could further improve the performance of the parts in hot environments. But is this even possible with thin airplane parts? No warping or sagging allowed. And is it even worth it? For this test, I'm going to compare this new high-temperature PLA from Polymaker to Overture PLA Pro, my current daily use material, and Polymaker's ASA, one of the challenging higher temperature printing materials with favorable mechanical properties. And I'm using my Bamboo Lab P1S for printing all of the parts in this test. Polymaker is not the first to come up with this high temperature PLA. Protopasta has a similar product that's been around since at least 2020. And Colorfabb has their HP material, used to be called HT material, which is the base material for their foaming lightweight PLA HT. I did a video about this foaming lightweight PLA HT, where it performed better than anticipated. Cooked the parts to over 72 degrees C for over an hour. Check it out. And I am working on a follow-up video to compare it to the foaming lightweight ASA from Colorfabb and Bamboo. So stay tuned, let's take care of this stuff first. From the Polymaker High Temp PLA product page, it says, HT-PLA runs flawlessly on most FDM printers. Using standard PLA settings, no upgrades or tuning needed. And recommended print settings do look the same as PLA or PLA+. I will print the HT-PLA and the Control PLA with the same settings. Pretty good direct one-for-one comparison. So using my usual SoarKraft PLA settings and test part from my website, I used PrusaSlicer in this case and imported these all in. If you don't know how to use PrusaSlicer or have a different printer, use my how-to video to get started. This method works the same with most any material and most any printer. And my ASA configuration I used in this video is posted here too. For the high temp PLA, the only alterations I did to these settings were increasing the nozzle temp to 220 and set the seam position to nearest for fins, which is a typical thing I do for my parts. I just kind of do it out of habit. Slice and print. I'm using a Bamboo P1S with a smooth PEI print plate and glue stick. Overkill for PLA, but I'm going to print all the parts on this machine. Check the test part for thickness, 0.41 millimeter single wall and 0.82 millimeter double wall. Perfect. I highly recommend marking parts to keep everything straight. I then proceeded to print a single left horizontal tail fin from my RoughGen airframe, which I'll use to compare the actual stiffness of a thin wall printed part, and a single wingtip for the hot car test, as well as print quality and surface finish. And any additional printing will use these files, settings, and this printer for everything. All right, let's get to the printing results and the testing. Looking at print quality between the different materials, I can compare dimensional accuracy, weight, surface quality, bridging, warping, and in my parts, the hinge area. So dimensionally, all the parts, as printed, look the same. All are within 1/10 of a millimeter of each other, which is pretty good. No shrinkage on the large dimensions, X, Y, and Z. But we can remeasure this after the heat test. Next, I measured the weight of the fins and of the tips and compared the magnitude of their differences, where the HT-PLA parts are 4% heavier and the ASA is 9% lighter, which comes close to matching the spec sheet reported densities. And even though the parts are different weights, the volume or wall thickness is within spec, which is important for my bin test later. Next up is surface finish. A quick look at the overture parts. Not perfect, but very nice. Surface quality of the high temperature PLA is amazing, but pretty much identical to the regular PLA. Almost impossible to tell apart. Bridging is identical. Zero warping on the bed surface. And hinges just like PLA Pro. And lastly, the high temp PLA did have some wisps when printing multiple parts, but not too bad. Switching to the ASA parts, which is relatively new to me, they turned out pretty good. I did the whole wall thickness size deal and got some reasonable results without too much effort, but I was a little disappointed with the initial surface finish. Easier to see these issues in the right light. Not exactly what I want, but not terrible. Bridging was pretty good. A tiny bit of warping, but not very much. The ASA hinges were a bit brittle, but still could be made. Just score the line and go slow. And always, no matter the material, use silicone hinges. Good to 200 miles an hour. Multiple part printing with ASA seems to work just fine. In fact, surprisingly, the surface finish looks way better, which means it can be fixed, and I can test to see if it affects the stiffness. Last test prep step I wanted to do was add a little flat spray paint, one even coat. All three came out nice. A worst case heat and sun test. All right, with all the parts printed, we can move on to testing. Test day was a nice 100 degrees Fahrenheit, and the truck was nice and hot. I laid the test pieces out on the dashboard, took some quick initial temperatures, and started the stopwatch. I should have started the timer the second I put the parts in place, because just getting the temp reading was enough exposure. 45 seconds in and the PLA Pro was already having a problem. 2 minutes into a 2-hour test, and the PLA Pro is already cooked. The other two still look fine. We'll check back in 15 minutes. While those parts are baking, let's compare stiffness of the different materials with actual parts. A good-looking, well-formed part may not necessarily be a strong part, but you can check it by measuring the force at a given distance on a group of samples. Sort of like measuring the stiffness of a spring, which gives the spring constant. It's a pretty crude setup, and it gives very specific values for one particular part, but a simple, non-destructive, repeatable test that has been surprisingly consistent, with enough resolution to see even minor differences. Change one variable and see what happens. Iterate, test again, and build on improvements, and not just relying on feel and aesthetics. So why am I doing this if Polymaker has supplied an extensive list of modulus values? The short answer is the spec sheet modulus values work for the filament on the spool, but not necessarily for the part printed with it. Polymaker is trying, but there are just too many variables unaccounted for with this table. Polymaker's XY value for the PLA blend to be higher than a pure PLA seemed to be overly optimistic, so I used the Z value instead. And then there is the disclaimer, which basically says that these are marketing values and actual values may vary significantly with printing conditions. Again, Polymaker is trying, it's just this is really complicated. So again, stiffness and modulus are not equal, but the magnitude of my measurement should at least scale with the magnitude of the spec sheet modulus, allowing me to compare and adjust to see if better values are possible. Alright, enough nerding out, let's get back to breaking and melting stuff. Here is one example of each type of material. Again, stiffness and modulus are not the same, but I'm going to compare them anyways. By scaling and normalizing my stiffness values to the better known PLA, which is not exact, but close enough, and comparing the HT-PLA stiffness value, disappointing and well below what was expected. But all the samples, even the multi-part prints, were consistent, and within 2% of this value. The ASA value for a single printed fin was a little low, and the better looking multi-part print ended up being a little lower still. but the parts were slightly underweight compared to a single printed part. We'll go with the lower value for now, but I see some settings tuning in my future for ASA. But we'll leave that for another video. The HT-PLA has a much bigger gap to make up, and it's kind of the focus of this video, so let's concentrate on it. And I will look at nozzle temperature to start with. The initial value was 220, so I tried 215, even though I know down is the wrong way to go, 230, which closed the gap significantly, and then pushed it even further to 240, which started to go in the wrong direction. Could try in-between values or variations of print and fan speeds, but 230 nozzle temp looks to be a much better choice. A quick weight check and it's heavier by 1%, which accounts for some of these gains and sort of distorts this comparison, but I would want to see what fan speed changes and print speed changes do before dialing in the wall thickness and flow ratio. This also shows how much this HT-PLA material properties vary with minor temperature changes, and how these two good-looking identical parts could be so different in stiffness. Oh, there's my timer. Let's get back to the hot car test and see how those parts are doing. So we're about 15 minutes in, and the PLA Pro is the shape of the dashboard. The HT-PLA and the SAS both still look good. No noticeable warping or feature distortion. The parts are in the 80 to 85C range, with the black strip in the 90 to 95 range. But this is just a cheap laser thermometer. Accuracy could significantly vary. We'll check back at the half-hour mark. A half hour in, and the HT-PLA might be having a slight droop. The ASA still looks pretty crisp. The aileron slot on the HT-PLA might be starting to distort also. Temperatures are still running about the same. We'll check back in at the 45-minute mark. We're at the 45-minute mark now. It's still really hot. The HT-PLA hasn't gotten any worse. And the ASA still looks pretty crisp. And the temperatures are still about the same. So we'll check back at a full hour. Here we are at an hour, and I did just move my truck. There was a tree about to cast a shadow on it, and I didn't want to interrupt my test. Still nice and toasty. Still running pretty similar temperatures. So at an hour 15, the parts don't seem to be changing much. Same temperatures. So let's just go to the end. So after 2 hours of cooking and some final temperature checks, I transferred the tips to a flat piece of cardboard so I could get them out of the direct sun and heat to let them cool down slowly. And I let them gradually cool down before taking them inside. Under my studio lights, the PLA Pro damage looks very familiar, but I was surprised that the painted area was not more affected. So while the HT-PLA is not a mess like the PLA Pro part, it does show signs of distortion and warping. There is some slight oil canning on the surfaces, and some irregularity in the trailing edge. And the interesting part about the trailing edge is it's not a droop, it looks like it's a buckling. And here you can see the oil canning a little bit better. It's not much, and if this was a backyard planter or a dashboard bobblehead, it would probably be just fine. But any warp or twist to a fin or a wing panel will cause major changes to how it flies. And here is the ASA part. Top and bottom, it looks just fine. Even the painted area. So looking at the HT-PLA parts again, I wondered if the paint strip heated up and annealed the part faster than the material around it. So I wasn't completely satisfied yet, and I had a second day of 100-degree temperatures. I wanted to see if I could anneal parts without damaging them and see what it did to the mechanical properties. I do have a decent epoxy cure oven I can use if this works, but it's not as fun as a hot car, and no way to see the parts while they're cooking. I have 3 HT-PLA and 2 ASA fins with known dimensions and stiffness values. My makeshift dashboard parts cooker had the parts up to above 80 degrees C in minutes. I also varied the orientation a little to see if it mattered. After a half hour of cooking, here's what the parts looked like. Notice that the control surface on all the HT-PLA parts have sagged, but not the ASA. At a half an hour, I started to pull the HTP parts out. Again at 45 minutes. And then the final one cooked for a full hour. And I let them slowly cool down. Other than the control surface sag, there was no other obvious warping or distortions. I couldn't really tell if the trailing edge was bent, but it looked okay. And even dimensionally, they were mostly unchanged. The ASA parts looked unchanged. And on the stiffness tester, the ASA measured exactly the same values as it did before. Kind of boring, but it means the ASA parts passed the hot car test. Alright, so here's where I'm hoping this HT-PLA will shine. Improved mechanical properties after annealing. It's a huge pain to do this secondary process, but if the results are a better, stronger part, then it might be worth it. Ah! That didn't sound good. So at 42 thousandths deflection, it failed at 81 newtons. Well below the 98 it reached before. Maybe it was a fluke. Keep testing, see what happens. Wow, 42 thousandths and 80 newtons again.
Okay.
This may sound stupid, but what an exciting result.
It's not looking so hot.
I was so eager to try the last sample, I didn't make sure that the dial indicator was positioned right. And the zero was a little off. And it fails at 81.4 and 47 thousandths displacement. Still really close to the exact same value, which is way down here if you look at it on the stiffness chart. Alright, so what does this all mean? So I really did want this new high temp PLA to work. Easy printing on any machine, non-toxic. Oh, it sounds fantastic. And the initial parts look really good. I could live with it being heavier and not as strong as regular PLA. A heat deflection temperature of 80 would be quite agreeable. But this is a deal breaker. Accidentally cooking your plane and making it more fragile might be worse than an obvious problem. If the goal is to print an airplane that can survive a trip in one of these, but still do this, then the ASA is the clear winner of this round. Difficult and toxic printing leave ASA open to other possible contenders. But for now, I'm going to leave the HT-PLA for the backyard planters and the dashboard bobbleheads. Well, that's more than enough for now. Check out my website for airplane files and material print settings. More videos on the way. Thanks for watching, and see you next time. That was awesome.